Howdy, welcome to the Smart Grid Center webinar titled Updates on Geomagnetic Disturbance Research, State Estimation, Integrated Geomagnetically Induced Currents and Harmonics Analysis, and the latest G5 storm. I'm Andrea Kisné from the Smart Grid Center. First, let me ask you to send questions in the Q&A window anytime to get those answered at the end of the talk, unless it's a clarifying question that may be answered during the talk. Or raise your hand with the hand button in the Zoom window, and I will allow you to unmute yourself to ask questions or make comments at the end of the talk. The presenter today is Dr. Jonathan Snodgrass, Senior Research Engineer at Texas A&M University, working under Dr. Thomas Overby in the area of large-scale electric power systems. He received his bachelor and master degrees at Texas A&M University and master's and PhD degrees at the University of Wisconsin-Madison, all in electrical engineering. His primary research area is in power system network planning and resilience, with current projects focusing on modeling impact of high-impact low-frequency events, such as geomagnetic and electromagnetic pulse disturbance on the electric grids. His other research areas include EV integration, combined transmission and distribution system simulations, optimization, power system markets, and microgrids. He also worked for 2 years at Zachry Engineering Corporation in Amarillo, Texas, designing simple and combined cycle natural gas generating plants. Dr. Snodgrass, take it away.
Awesome. Thank you, Andrea. As Andrea said, I'm Jonathan Snodgrass, Senior Research Engineer here at Texas A&M. And this is my second webinar on geomagnetic disturbances. I presented one about a year ago. So if you've, I tried to do some review so that way it wouldn't be, that way there'd be some background. So I apologize if there's a little bit of overlap here. But I wanted to first actually start with, sorry, bottom thing, of course. So I want to make this a little bit more interactive. And as Andrea mentioned, if you have clarifying questions, please feel free to ask during my presentation. And I want to start off with a little poll the audience. So first, make sure your hand raise button works. So I see 2 people have their hands raised. Great. It's this little button, at least this is what it looked like on my screen, at the bottom of your screen. So hit that and I'll, A, make sure you're awake, and B, make sure everyone can find it. Great. I see people's hands starting to raise. Excellent. Okay, so I got about 15, and I realize some of you all are audio only, so you can't raise your hand, and et cetera, et cetera. Okay, so I can lower everyone's hands too to make things a little bit easier as well. So my first question is, please raise your virtual Zoom hand if you have at least a rudimentary knowledge of geomagnetic disturbances, GMDs, geomagnetically induced currents, GICs, and their effects on the power grid. And you can define rudimentary however you want to. Great. Okay, so about quite a few of y'all, at least half of the people tuning in have a pretty good understanding, or at least a rudimentary knowledge. Great, which makes sense because y'all are joining this webinar. Raise your hands if you have conducted a TPL study yourself, like you were the lead, either the lead or the main engineer on a TPL study. So I'll raise my hand as well. Give it a couple minutes, about 8 or 9, and leave your hands up. And then add your hand to that list if you either were the lead or you also assisted with the TPL study. Okay, so a couple other hands pop up. So raise your hands if you've read the results of a TPL 007 study or some other GMD assessment. Cool, I see the hands start to come up. Okay, and so finally, add your hand to the list if you've at least read parts of the NERC TPL 007 standard. Okay, awesome. Great. Perfect. Okay. And then finally, I'm going to lower everyone's hands. And finally, raise your hand if you remember if you attended my webinar about a year ago. If you don't remember, that's fine. So, obviously, I was here. See a hand. Small number of hands. Okay, good. So it's a pretty fresh crowd, which is great. So that way, I won't be repeating too much information for too many people. Excellent. So I will start by kind of a high level overview, and I apologize, my camera's here, but my monitor's here. So if I'm not looking directly at y'all, that's the reason why. So GMD analysis has four major components: modeling, data, simulations, and mitigation. And as those who've done a TPL 007 study, you know this very well. The current state of the art is for modeling. You need additional information compared to a regular power flow analysis. You need geocoordinates, and you need additional parameters for transmission lines, transformers, and substations. Pretty straightforward for those who've already done it. For extra data, in addition to the data for the modeling, you also need some sort of E-field information, and you can either calculate that or you can use the NERC benchmark waveform. And the steady state, the simulation that's usually done during a standard GMD analysis is typically steady state. Some people I've talked to have done transient stability, but that's less common. It's usually a steady state worst case, and then if needed, a thermal and harmonics analysis. And the mitigation is only if needed. So I want to touch on kind of a very high level overview of the research that's being done here at A&M. So in addition to everything that's the standard that I did during a TPL study that we did for a partner utility of ours, I want to touch on the additional modeling. So as y'all know, it's a challenge. So a little more audience participation. Raise your hand if you had, for those who did or assisted with the TPL study, raise your hand if you had substantial difficulties in getting accurate information about geocoordinates, modeling parameters, say the DC resistances for transmission lines, or the transformer types, substation grounding resistances. I'd say for us. Right. Okay, so I see about 8 of y'all raising your hand. So that's a pretty common pain point, it seems, that it was hard to get this information. And so raise your hand if you had to rely on some of the NERC standards, as well as just kind of default parameters that were in either Power World or PSSC or PSLF for transformer types, K factors, et cetera, et cetera. I know we had to do some of that as well. A lot more hands. Okay, correct. So this is past research that we've done, but Tom, Professor Overby, and Adam, Professor Birchfield, did some research on sensitivity analysis for determining which of those parameters have a higher impact on your GMD analysis. So definitely go in and read that paper from Tom and Adam if you get a chance. I read it. It's a great paper. We're also introducing additional transient stability modeling in the GMD analysis, and that's a different topic. Adam might present a webinar at some point in the future. Hopefully we'll see. He's presented, he and his student Luke just submitted a couple papers on voltage stability and voltage stability and transient stability analysis with GMD modeling, and that's another thing. So transformer thermal models and harmonic models, and I'll get to that in a little bit of a second. So the data, and this is what my previous webinar talked about. So if you're interested, you can go back and watch the recording. We're doing more than just the standard peak, 8 volts per kilometer, 12 volts per kilometer analysis from the TPL study. We're looking at, what would a worst case scenario be? And I touched on this in my previous webinar. The highlights were, before she passed away, our collaborator CPI Jen Gannon had created this synthesized Carrington waveform that is kind of a once in 100 year, once in 1,000 year potentially storm. I guess more like once in 100 year storm modeling, and then we're even looking at what would a once in 1,000 year storm be, and so that's kind of some ongoing analysis, but also mostly looking at spatiotemporally varying E-field waveforms. And I talked about this in my previous webinar, but as y'all know, just even looking at the NERC benchmark, GMDs are very dynamic in the sense of they change rapidly. The magnitude fluctuates, the angle can change very quickly. And because of that, just doing, well, first of all, defining what worst case is also difficult, because since the GICs will be changing in a large storm, what is worst case 1 minute can change very rapidly to the next minute. So that's the type of analysis we've been doing here, and looking at the importance of spatiotemporal variations on GMD analysis. And we published a couple papers about that. We're also looking at converting B field to E field waveforms, in collaboration a little bit with NOAA, and we've had a couple talks at the USGS. And that includes the Earth conductivity modeling, which we've talked about with EPRI. And specifically, we've been looking a lot in simulations. So incorporating the spatial temporal variations in E and B fields, we're looking at time step simulation, as well as transient stability. And I see Tom on the call. He and Bob have been doing a lot of great work on an integrated harmonics and thermal analysis, integrating the EPRI's GIC Harm and ETTM tools with PowerWorld to be able to do integrated assessment of GMD analysis instead of, as I mentioned before, instead of doing the thermal and the thermal analysis and the harmonics analysis on an as needed basis, instead being able to just incorporate that directly into the GIC study, so that way you don't wind up accidentally missing something, because there's still some debate about, whether the 75 amps per phase is the proper threshold and all of that. So I don't need to get into those discussions, but and I'll go into a bit more detail on this, but GIC state estimation is something that we've also been doing for simulation. So using the GIC measurements to calculate the E field. And then once you have an E field, an estimated E field, then you can use that to calculate GIC flows on devices that don't have GIC monitors. So we have some ongoing work to determine how to best strategies to mitigate or reduce GICs. And there's the standard GIC blockers. Those are good and those are needed. We also have, people have proposed topology changes, so line switching, unit commitment, etc. There's also been talk about if there's a high level of harmonics, what changes need to be made to relaying schemes. Do we need to change out CTs? Do we need to, what changes need to be made such that the harmonics don't affect the relays as much? And I realized that I kind of put the cart before the horse on purpose, because I know that about half of you said that you had a lot of experience with GMD, and it looks like about half of you don't. So I'm going to back up and catch up the people who are probably lost at this point. So I'll ask, what are geomagnetic disturbances? Why do they matter? Where do they come from? And how are they related to the pretty lights in the sky? And then we'll look at the two big updates we've had since the last year, which is our state estimation and our integrated assessment tool with EPRI. Although the assessment tool will be a bit more high level. So first, I want to give a plug for our short course. It's scheduled for March 18th through 19th next year here at the A&M campus. Your instructors will be your very own Tom Overby, who's on the call, Bob Arrett, who I don't see on the call, but he will be there, as well as a couple others from EPRI who will be assisting, and then myself. And then there's talk of having a OpenDSS training immediately following this webinar, but that hasn't been officially decided yet. But there's a possibility of getting a 2-for-1 deal in terms of 1 travel, 2 courses, but 2 registrations. So let's back up for a second. So I guess I'll go for a little bit more, then I'll pause for clarifying questions. So backing up to the 10 million mile view, what is space weather? So just like the Earth, the sun has its own weather. It's actually, the sun it looks fairly stable in the sky, but those who know space weather know it's actually very tumultuous. There are sunspots that you can fit, hundreds of Earths in. So the solar cycle is around 11 years compared to, Earth has a 12-month, year-long weather cycle, spring, fall, winter, summer. Unless you're in Texas, in which case we have summer, 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 and then Christmas. But so the Earth has a continuous stream of plasma called the solar wind. And usually the solar wind is fairly mild. But when you have a large sunspot, you could have these large release of billions of tons of matter of coronal, what are called coronal mass ejections. And these are mostly what cause geomagnetic disturbances. So a GMD occurs when a CME hits the Earth. And just like a hurricane, a GMD ranges from class 1 or G1 to G5. And unlike a hurricane, it's not a straightforward determining what a G1 to a G5 will be. And I think we had an undergrad paper as well as one of Dr. Davis's students, Rhett Guthrie, published a paper kind of explaining a bit more, or he's working on some work kind of better defining, creating some better definitions of what G1 to G5 would be. And so like a hurricane, it has to be maximum sustained winds, whereas a G5 storm can occur when the peak magnetic field change is within a certain range, but that peak might only be for a very small amount of time. Whereas there could be a storm that's a lower storm, say G3, G4, that might have a much longer sustained higher electric field that actually might wind up being more worse for, say, transformer thermal heating. So there's some discussion and some research here at A&M about kind of better defining the severity of a geomagnetic disturbance, but that's not the topic of this webinar. But this picture here, let me see if I can pull out there you go, there's my pointer. So the sun has, this is a very cartoonish solar flare, but it gets discharged, and the charged magnetic particles from the solar wind hit the CME, they hit the magnetosphere of the Earth, and they, as you can see, it compresses the magnetic field on the near side and it expands out on the far side. And those changes can cause problems. And so we're most familiar, of course, with the problems caused to the electric grid. We have, GICs in our power system, but these the space weather also impacts more than just the electric grid. It can impact spacecraft electronics if they're not shielded properly. It can affect GPS because it can disrupt the GPS signals, and so it can affect aviation, communication, potentially PMUs. If it's severe enough, it can also affect undersea cables, as well as it can also cause currents flowing in pipelines, just like it can cause the ascents, in a sense, similar to GICs, but on pipelines as well. If the cathodic protection isn't proper, it can cause issues there. But so what causes a GIC? And like I mentioned, CME is ejected from the sun, and so then the Earth experiences a changing magnetic field. And for those who remember Fourier's law, or not Fourier, Ampere's law, sorry. Ampere's law, a changing magnetic field causes a changing electric field. And the Earth itself is a giant conductor, except it's a very resistive conductor. But if you have a changing magnetic field, the Earth's magnetic field is changing more rapidly than it normally does, then it can induce a changing electric field in the Earth itself. And this electric field well, let me back up a second. So first, the changing magnetic field interacts with the deep Earth conductivity, which there's a lot of uncertainty with the deep Earth conductivity models, which is the subject of ongoing work at USGS. But then this causes an induced electric field at the surface, which normally we wouldn't care about this, because if you have, say, 3, 4, 8, 12 volts per kilometer, that's normally not a problem, unless you have a 200-300 mile or kilometer-mile long transmission line that now has a potential difference between from bus and to bus of say 3,000 volts, for example, for a bad case. So now you have your classic example of, you have a transmission line, which is a resistor in this case because it's quasi DC. You have a resistor, you have a voltage source of the ground, and you have paths to ground via transformers, the grounded transformers. And so now you have a complete circuit with the voltage source, and so you get currents flowing. And so these currents are geomagnetically induced currents, or GICs, and they flow in transmission lines. The E field can also be directly induced in the transmission line, and there's some of both. There's some direct induced E field in the transmission line. There's some E field induced in the ground, and that flows up through the grounded transformers. And that is a basic summary of GIC. So for those who know PPL studies, you could have given this part as well, but this is for those who aren't intimately acquainted with GMDs. So I'll mention one more thing, and then I'll pause for some initial questions. So as I mentioned, the GMD causes geomagnetically induced currents, or GICs. And this is kind of a high-level picture of what I just described. So since the changes in Earth's magnetic field are fairly slow in comparison to the 60 hertz power system frequency, they're pretty low frequency. They're sub 1 hertz. They're like 0.1 and lower hertz. So they're quasi-DC, since they're several orders of magnitude lower than 60 hertz. So we model them in the system as DC current, because in comparison to 60 hertz, they can be viewed as DC. And so when you have your normal 60 hertz sine wave on the grid, whether it's voltage or current, in this case current, you have your 60 hertz fundamental current on the grid. Sorry, my camera just got blurry there for a second. There we go. You have your fundamental 60 hertz frequency, and then when you add on a DC offset to this, you have transformers that can enter half cycle saturation. And I'll show pictures of this in a second, but when you have half cycle saturation, when it gets bad enough, let's back up. For mild cases, you kind of get rounding or flattening of the top of the sinusoid, but the more saturated a transformer core will get, the more the top half cycle of the sine wave starts to look like a square wave. And as you remember from Fourier analysis, square wave consists of multiple harmonics. And so, you can model it as multiple harmonics. So this half cycle saturation causes harmonics in transformers. And so harmonics can cause several issues. One is they can cause nuisance tripping in relays. They also, since you have a non-sinusoidal current in the transformer, the secondary winding of the transformer, or the secondary, no, let's back that up. Yes, you have you have non-fundamental frequency current. So you get increased VAR losses of the transformer. You start to get the transformers the fundamental frequency, the fundamental component of the voltage can start to drop because of the harmonics. And we model this as increase in VAR losses on the transformer. And so if you have a substantial increase in VAR consumption of the transformers, you can have voltage stability problems. And so thankfully, we haven't had a storm big enough to cause voltage stability problems, and there's some debate as to whether we even could get a storm big enough to cause voltage stability problems, but that's part of the subject of our ongoing research, is to say how big of a storm would we need to have in order to have voltage instability in the grid, and is such a storm possible? Meaning, is it within the realm of physical reality to have such a storm? And of course, this isn't even touching on EMP waveforms, which are a different, similar. They're a different beast, but they're similar. So I'm going to pause here for a second. I know I've talked quite a bit. Does anyone have any clarifying questions? And I might, if I might say the answer is great question. That's in my next 3 slides or whatever. I see Barry just raised his hand. Hey, Barry, you can unmute yourself and talk now.
Okay, can you hear me?
Loud and clear.
Perfect. Hey, I was wondering if you could comment just briefly on GMD magnitude, potential magnitude. You went through the categories there, but put it in relation to EMP, or if there's a difference in terms of magnitude and severity, et cetera.
Yep, great question. Actually, great question. So, I could speak a lot on this, but I'll try to keep it short. So the NERC benchmark specifies 8 volts per kilometer with a hotspot of 12 volts per kilometer. The it was recently declassified, I think back in 2016 or 2017, there was a E3 waveform, I think, that got up to 85 volts per kilometer. So E3 can be quite a bit higher than a GMD, but an E3 waveform is usually done within a couple of minutes. And usually the peak of an E3, the worst part of an EMP E3 usually is within a minute, I think, roughly. I mean, there's not a lot of EMP research is classified, and so it's kind of hard to publish some of that work in some regards, but a GMD is lower magnitude, but higher, lower magnitude, but much longer duration, whereas an E3 is higher duration, but much shorter magnitude. And the research question is, does even that shorter duration E3, does it cause enough voltage stability problems to cause, say, cascading failures or black out the grid? Now, that's another subject of ongoing research here, but of course, then it becomes a security issue, because if the answer is yes, then people want to know, how do you mitigate? But then, of course, you have to be careful that you don't reveal too much information about where detonating an EMP would be most vulnerable to the grid. So we always, here at ANA, we always play defense. We're always saying, how can we make the grid better? But we still have to run simulations of what an EMP would do on the grid in order to do that. So does that answer your question?
Absolutely. Thank you much.
Great. I see Ahmed. Question.
Can you hear me?
Yes, I can hear you.
Oh, great. And yeah, I saw mainly the voltage, right? You change the voltage and the power. Is there any real power also change, or does it supply any real power? How do you model it?
Great question. So, no, it does not supply, GICs don't supply real power, in the sense of real power meaning 60 hertz voltage that is in phase with 60 hertz current. So it's all, in a sense, it's all reactive, because the frequency of the GIC current is so low that there's no fundamental DC frequency of the voltage to interact with. That does raise the question, though. One thing that we're looking at potentially doing is maybe using power electronics both to mitigate, as well as potentially, what can we use power electronics to do to mitigate that? But to answer your question, the answer is no. It's only reactive power.
All right, thank you.
Mm-hmm. All right. Anyone else have questions? I see. I saw a hand go up and then down. All right, cool. I'll keep moving because I got one more question. I'll take one more question and then we'll keep moving. So I'm about halfway through the presentation, and about 3:30. Yes, Hassan.
You mentioned transient stability. You will talk about that, because these are quasi steady state waveform or signals. How transient stability comes to play? Thank you.
Yes. So transient stability is important for several reasons. One is that you should definitely watch my webinar from last time, because the GIC wave, or the E-field waveforms are definitely not quasi steady state. They're quasi DC, in the sense that at a specific time, the current induced in the line is quasi DC, but the magnitude of the electric field changes quite rapidly, and rapidly meaning on the order of seconds to minutes, but seconds to minutes is definitely not steady state.
I'm sorry for the misuse of the word. Yes, we have measurement sensors that measures GIC at SDG&E in a couple of locations at the neutral transformer. We see that waveform and the quasi DC. I was trying to find unmute. That's why I misused the word. Sorry about that. But the question is, at that time scale, time constant, what is my question was about the transient stability, transient dynamic stability, transient stability. How does it relate to that? That I don't understand, because that is not the time scale For
Mhm.
for transient stability, we are talking about cycles, and it is basically very short compared to the changes that we see on that quasi DC waveform that we see. Thank you.
Right, right. So, like I was mentioning, so the changes on the current itself can be slow, but they can be faster, depending on the storm. And so for the NERC benchmark, the E field changes quite a bit from minute to minute. The biggest thing to answer your question is it's for simulation. So say you have a once in 1,000-year storm that's substantially worse than the NERC benchmark event, and your steady state assumptions start to break down, and so you have when you're nearing voltage stability limits, you need to start you can't just do a static power flow or steady state power flow. What we found is that the power flow might converge in the time step simulation that we did. And this is, I presented a little bit on this in my previous webinar, and I might be able to talk more in the future, but it's not the subject of today's webinar. I'd love to see if Professor Adam Birchfield could talk more on this, because he's kind of taking the reins on this. But what we found is that some preliminary work we did about a year ago found that the power flow might converge. Excuse me. But then when you run transient stability, you find that it's actually the system's actually unstable, or vice versa. The power flow might not converge because the change in operating point is too big between the steps, because the E field is changing so quickly. But the transient stability shows that it actually might still be stable. So it's to answer your question, it's not an issue for the moderate to smaller storms we've seen in the last 20, 30 years, but for something like a Carrington event or a super storm event, we would want to look at transient stability and not just steady state. But
I asked this question because the impact of GMC or GIC is usually we look at it as for the saturation of the transformer, which has thermal effect, and also harmonics.
Yep.
And which part of it induces that instability that you are talking, you are concerned with, because these are the time scale for thermal impact is, of course, it is at least minutes. It is not cycle, and maybe voltage stability is the issue, but still you need the reactive deficiency for voltage stability. So I cannot relate this low frequency DC, quasi DC signals to transient stability. But anyway, that's my concept. Thank you.
Yeah, no, good question. So, and I saw Tom pipe up in the Q&A, and so he said that he was reminding me as I should clarify that right now we don't use stability for GMD because, like you said, the timescales usually are pretty small. We have done some research here at A&M looking at when you start getting a large scale GMD event that exceeds the NERC benchmark. What the research that we did, as I mentioned in my introduction, is at what level of storm do you have to get to where the grid becomes has voltage instability. And in order to test that, we ran some voltage stability runs with large time steps because we weren't talking, like you said, we're not talking line tripping and things we're not talking smaller scale. We wound up increasing the time step a good bit. But we found that just a simple time step simulation in like a steady state power flow wasn't capturing the whole picture. So that's that to answer your question, it would be more for like a extreme event analysis. But that's, yeah. Okay. I'm going to go ahead and keep on going for the sake of time as well. Thanks everyone for asking those great clarifying questions. Right. So we actually did have a G5 storm, most of y'all probably know, back in May of this year. It started on May 10th and it continued some into May 11th. So this was the largest storm by some measures to occur since 2000, since for sure 2000, potentially since 1989, since the big storm in Quebec. So several relays did trip due to harmonics, mostly I think capacitor and capacitor bank relays tripped. I don't have the details. Bob at EPRI and his team are working with utilities, so still trying to figure out exactly whether it was just nuisance tripping or whether it was actually GMD cause, where there's an underlying. They're still doing root cause analysis on this, but there definitely were there were more trips observed during this storm than normally would be expected. So we're strongly suspecting that this is due to the GMD storm. The good news is that based off of the improved modeling, simulation, and some mitigation measures that we had put in place after 1989, there weren't any, it was a non-event in the sense of there weren't any blackouts, outages, damage that we know of, et cetera. But there's still analysis ongoing. But one fun part is that with a camera, at least, the Aurora Borealis was actually visible all the way as far south as College Station, Texas, which has not occurred in a very long time. This picture is actually taken by our very own graduate student, Rhett Guthrie, with his iPhone, just outside. He got a picture. Of course, it's nothing nearly as fantastic as our friends and colleagues up in the upper Midwest or Alaska or New England, where it was quite the spectacular view. The pictures posted all over social media of the sky basically on fire. But while the lights were absolutely pretty in the sky, we were definitely excited, both, hoping that there was nothing wrong happened to the grid, and then nothing was, thankfully. But the nice thing about this larger storm is that it gave us a lot of data that we had been looking for. So in the sense of, I'll get to that one. No, actually, I'll show that video real fast. So there hasn't really been a large storm, as I mentioned, in the last 20 years. And so since the 89 storm, we've put in, we meaning utilities, Texas A&M, et cetera, lots of people have put in GIC monitors, they've put in magnetometers, we've done USGS has done a tremendous amount of work on an updated deep earth conductivity, resistivity model, and updating from 1D to 3D conductivity models. And so this storm finally kind of gave a test of all of that equipment. And so here's a quick little video. PowerPoint wouldn't let me embed it, so I'm going to post it on YouTube and include the YouTube link in the slides. But I'll let it play while I'm talking. But this data is from NOAA. It's minute resolution data that we downloaded from NOAA. So I want to give credit where credit is due. And then we ran it through. We did power system analysis on this. Now, if you notice, it's like 400, it's millivolts. NOAA measures it in millivolts per kilometer instead of volts per kilometer. So we're going to change the scale before we publish our papers on this, just to make it a little less confusing. But just wanted to explain why there's a 400 number. And so the pink circles are the GIC flows through any branch, so whether that's a transformer or a line. And the color contour, and now things are starting to get interesting. So right around 3-4 o'clock in the morning, you can see how the GIC's flows are varying in the system. And one thing to note is it's even on the minute level, the GIC flows vary quite drastically. And the E field changes quite drastically, as do the GIC flows. Now, keep in mind, this is Texas, so we're talking, less than half of a volt per kilometer. But in some of the more northerly states, they were seeing several volts per kilometer calculated E field. I mean, we took this was calculated by NOAA, taking the B field measurements and running it through their B to E calculations. Let's go back to my slide. Go. There you go. Y'all still see my screen? Raise your hand if you can still see my screen. Great. Okay, perfect. There's always the danger of whenever you close away from one screen, you get technical difficulties. Okay. So I already mentioned this earlier. This was a slide from my earlier presentation just to explain the half cycle saturation. So I will continue on this. And for this is, if you have questions about this, we have time at the end, I can dive into a little bit more. But this is from a sort of view from my previous presentation for those who weren't able to attend. And this is the impact, and I've already talked about this as well. Okay, so a quick overview of the work that we've done here in the last 10 or 15 minutes. So first is we've developed over the last several years, we've developed synthetic, realistic but not real test systems for GMD modeling. Now, for our utility friends, this is less important for y'all because you have your real grid models. These are very useful for, let me back up. They're less useful for utilities, but still of some use. So say, for example, you're doing some, like if you're an ISO or large utility is doing some, some internal R&D, and you want to test some new GIC algorithm or some new GMD algorithm, or you want to look at something and you want to share both your data set and your results in your algorithm, you can share that using these synthetic test cases, which for researchers who want to publish, say, such as us, who want to publish our results, we won't ever release CEII data. We use our synthetic grids in order to be able to freely share our results, both the models, the data, and the results. And I talked about this a bit more in the previous webinar, but we are still continuing to run our Texas magnetometer network. And I'll have a slide on that. I'll talk more about the state estimation for about 10 minutes. And then we also have scenario simulations, and we're working on mitigation as well, as I mentioned, mitigation scenarios. So the magnetometer network was built out, CPI, computational physics, put this network together, and they operate it for us. So there are 5 locations on Texas A&M land, and one is right down the road here in Bryan. It's our sister city to College Station. And I want to show a quick picture of the May 10th event. This is believe in UTC. So if you're wondering why the time step here does not line up with the video from earlier, this is in UTC. Yes. So what you can notice is, and I included this this flat start in a sense, to show that the normal fluctuations in the Earth's magnetic field are fairly small, but there are some fluctuations. But you can see that even here in Texas, we saw 500-600 nanotesla variations. So from here to here, I'd have to zoom in to look exactly at the nanotesla per minute, but it was not a small storm. And we have a GIC monitor, research GIC monitor we've installed with the partner utility here, and we were able to, it was small, it was a couple amps, but we did record some neutral current on transformers here in Texas, which is a pretty rare event for transformers in Texas. And so I'm going to keep moving and looking at our hypothesis for the GIC state estimator. So the traditional GMD assessment goes kind of a ground up assessment. It looks at magnetic field measurements, B field measurements, and then from there we've created, y'all know this, but we've created a E field waveform, the NERC TPL007 benchmark event, and from B you go to E, from E you calculate the GICs, and from the GICs you then calculate system impacts. The problem with that, well, the challenge, I wouldn't say it's a problem, but the challenge is everyone raised their hand earlier saying it's hard to get models, it's hard to get data, it's hard to get accurate models. So our question is, can we reverse that? Can we, instead of saying B and then our output is system impact, can we look at system impact, can we look at the GIC measurements, and can we use the GIC measurements to back calculate the E field? And from there, then we have an E field measurement, and then we can use an E field measurement to calculate the GIC flows on other devices that don't have GIC measurement. Now, of course, this is still assuming that we have correct substation grounding resistances, transformer models, et cetera. But as part of this approach, this is the next step. We can use the state estimation approach to, plus a sensitivity analysis to identify which measurement devices, which modeling parameters, et cetera, have the most impact on the GIC assessment. And therefore you could say these substations, the grounding on these substations has a very high impact on the results of the system. So you should go send some techs out there to do a follow potential measurement to calculate the updated substation grounding resistance. Or, we need to go try to find the old papers on this transformer, or go out there and put some, Rust-Oleum on the nameplate to try to figure out some more information about this transformer, to figure out, what core type it is, et cetera. Whether it's core form, shell form, et cetera. So state estimation, for those who've taken an undergraduate or some undergraduate or graduate course on power system, you probably learned about state estimation. So it's a weighted least squares linear state estimation, where you have measurements. Traditionally, these are your P and your Q measurements, and you're trying to estimate the voltage, magnitude, and phase angle. Sometimes voltage magnitude can be a measurement depending on how you do your state estimation. But in this case, we're doing it a little bit differently. So instead of a traditional state estimation where power, P and Q are your measurements, and then the voltage, I said this, voltage phase angle is your state, and it's typically an overdetermined system. You typically have more P and Q measurements than you need, and so therefore you can do things like bad data detection, or some rejection of error, or like measurement error, et cetera. In this case, it's a very underdetermined system. The number of it's underdetermined in the sense of the number of variables, the number of unknown GIC flows in the system is much higher than the number of known GIC flows. However, since the system is connected, and if we have a decent model, which could always be improved for the real grid model, we know that in E field, as far as an E field is mostly uniform across a certain area, that the E field, the GICs can be calculated once you know the E field. So in a sense, the number of states is the number of zones of an E field. And as the video I showed indicated, there you could kind of see the E field varying in about 2 or 3 zones across Texas, where the E field was most of its magnitude was mostly consistent. This is in the model. Granted, there's still model validation on the ground conductivity, but at least from the video I showed, there was 2, maybe 3 states, 3 zones, 3 E field zones in Texas. So what we've done is, let's see if I can go forward. We approximated about 5 zones. This is using our synthetic grid. We can also use the real grid as well. But we used about 5 different zones, and within each of those zones, we assume that the electric field is uniform. And so the question we are asking is, how many GIC measurements do you need in order to estimate the E field using neutral current monitors, GIC neutral current monitors? And just intuitively, the answer would be, if I was in person, I'd ask you to hold up your hands with how many measurements you think it needs. At least 2, because there's an X component and a Y component, or if you're doing polar, magnitude, and angle. So you have to have at least 2 measurements in order to get anything useful, and which is what we found. Anything less than 2, and the error basically becomes infinite. At 2 measurements, you can't really say anything about noise, but assuming a perfect model, and I laugh because everyone should be laughing at this point because no one has a perfect model, but assuming a perfect model with no noise, with 3 measurements, you're able to reproduce the E field with 2 numerical precision. So 10 to the -15th is basically the precision of double floating point. But everyone knows that perfect measurements are not realistic. But what we were doing is testing the hypothesis that you only need 3 measurements to do this, and the answer is it works. Once you start putting measurement noise in, you reach much more realistic levels or much more realistic error. So the way we did it is we have, in this case, a known E field that we use to calculate the GIC flows in the system. We then take the handful of GIC measurements as known quantities, add some noise to those, then use those measurements plus the noise to then back calculate what the expected E field would be using the state estimator and compare that with the initial E field that we used to calculate the GICs from the GICs for the measurements. Slightly confusing because this is simulation, but the eventual goal is to be able to do this in real time, or if you have GIC measurements coming in from the field, from your transformers, that you can then back estimate the E field and then do a calculation and a state estimation calculation of the GIC flows on the other parts of the system that don't have GIC measurement devices. And so the moral of the story is that it's still not a large number of devices that are needed per zone, and I say zone in quotes, meaning per area where the E field can be treated roughly as uniform, roughly. And that's, again, ongoing research to determine where do you draw those lines, what parts, clustering analysis of what parts of the grid can you consider the E field to be constant. So the NERC benchmark event assumes that it's a spatially uniform E field. We've shown that it's obviously not. So the question is, where do you put your zones, your GIC zones, your GMD zones, and from there, where do you place your measurements? So our ongoing research is looking at, and I want to leave time for questions, and I'll go over this in a second. Our ongoing research that we're looking at is optimal placement of these measurement devices. I know a lot of it is based off of just availability of transformers or real practical considerations, but there should at least be some analysis, which we're doing, to look at where would optimal locations be if you're going to place these measurements. Would they be more effective if placed in certain locations versus other locations? The answer is we're finding yes, and then we're working on an algorithm to more optimally place them. So, for example, a logical choice would be placing your GIC measurement devices at transformers that are more likely to see higher GIC, so you can have higher signal to noise ratio, for example. But that's one approach. But then what if this transformer only has high GIC flows for a certain couple of different storm types? What happens if there's a range of E field angles that cause low GICs on this transformer? So all these questions are things that we're working on answering. And then briefly, I'm touching on the integrated assessment tool. These are the slides I did from last time. I think during the short course, we'll have a whole part of the course dedicated to the integrated assessment tool. And I think there might be a future webinar between now and then kind of debuting this tool. But what it does is it's some work by EPRI and us here at A&M, led by Tom Overby and Bob Arrett, that integrates the NERC BDE tool, the EPRI BDE tool, sorry, EPRI's ETTM, EPRI's GIC Harm, and then the Power World GMD solver. So the GIC calculations plus the AC power flow that incorporates the increased reactive power consumption from the transformers. And so this is kind of a screenshot of some of those tools. And this is a flow chart of kind of how it works. We calculate the E field, which gets fed into Power World, which then sends, this is not from TXT and XLS anymore. It's a direct call from Power World to GIC Harm and soon to be ETTM. And then if needed, that information can get fed back into Power World. If the updated reactive power consumption of the transformers is increased, if the fidelity is increased by this harmonic analysis, they can get fed back into Power World as part of a closed loop. But the goal of this and what we've demonstrated is that instead of having to do all three of these pieces separately, instead of having to manually load for every single transformer, load in the files from Power World into GIC Harm, it can be with the push of one button in Power World, you can run a GMD analysis, a harmonic analysis, and a thermal analysis all at once for all of your transformers. Now it's going to take a while because harmonic analysis is fairly slow. But if you're doing this on a planning horizon, you could turn it loose and let it run for a few days, and then come back and you have your full assessment done. So I realize I'm 5 minutes out, and I've already asked for clarifying questions. So I want to again give a little plug for our short course, the 18th through the 19th, and ask if anyone else has any questions. leave that there while everyone thinks about their questions. You can raise your hand and I can allow you to unmute. Or you can type in the question box.
Hello.
Oh, Ahmed, did you have a question?
Yeah, not question. Can you show any result that the with GMD and without GMD, how it looks like?
Any results for what are you talking about?
Yeah, so let's say I simulate something. You say time step or time series, whatever you want. So time series simulation or even one instant with GMD and without GMD, how it looks like.
Yes, we have. We've published a couple of papers, most recently one journal paper in IAS, transactions in IAS, looking at, it was an analysis of a smaller storm. There's a G3, but we did that comparison kind of with and without GMD analysis. And that's something that we could do for this latest G5 storm. Now that we have the data, the answer is yes. Do I have it in this slide deck? No, but could we do it? Absolutely.
All right, I'll take a look.
Go ahead.
Yeah, I will take a look.
Awesome. Someone asked in the chat if what type of grid model does the state estimator need to perform the voltage estimation? Great question. So that is, it would be a standard GMD assessment model. So going back to, sorry, I'm going to give everyone whiplash. These. So it needs the GMD model. So it would need it needs geocoordinates, and it needs the parameters, the DC line resistance, the transformer type, and the substation grounding resistance. Now, what the state estimate, what we've done is we take that information. Apologies, hold on, whiplash again. I guess I could have just closed out of my PowerPoint and done this. So we use that to create these matrices. So the line conductance values, so the G inverse matrix, this phi matrix, to include the different transformer types, and the H matrix as well. So to answer your question, it would be if you have a GMD model in your simulation software, PowerWorld, PSSE, PSLF, Powered Simulator, you can create these matrices. You can use that model on the state estimator. Hopefully that answers your question. Oh, that's a great question. So Lee Min is asking, does the increased integration of renewable energy plants into the electric grid make it more vulnerable to damage from GMDs or GICs? Ha! You must have been listening to a conversation I was having with one of the top students today about this. Maybe. It depends on, the reason I'm pausing is because I could do a whole nother webinar on this. It depends on if they're IBRs, inverter-based resources, or if they're, say, type 2 or type 3 wind turbines. But more importantly, it depends on how they're operated. So if they're operated as unity power factor grid following inverters, converters, then yes, it will, because IBRs, if all the IBRs do is introduce or inject real power onto the grid, during a GMD, the transformers consume more VARs, and so the system needs to have more VAR, additional VARs being supplied, and so the IBRs wouldn't be able to do that. Now, grid following, if I said grid forming, I meant grid following. Sorry, grid following inverters. But if we have grid forming inverters with, say, a voltage, a QV droop, that would adjust the reactive power output of the in IBR-based generation to increase the VAR support or increase the VAR injection in order to maintain voltage, then that can help mitigate a lot of that. Part of the problem, though, is that the VAR capability of IBRs is typically lower than that of synchronous generators, because you have because the generators can can output for shorter durations. They can output higher current, like during a fault, but power electronic interface generation can typically only output extra current for a very short amount of time before, say, a crowbar circuit kicks in. I'll answer one more question, and then I know we're at 4 o'clock. Can the model program be used out of the box for lower latitudes outside of the U.S., e.g. the Caribbean? Will specific input for such locations be needed? No. So all the tools I talked about, the state estimator and the integrated assessment tool will work all over the U.S. as long as you have a GMD model for your system. No, all over the world. It'll work all over the world, including the Caribbean, South America, Asia, all of our Asia Pacific friends, Europe, as long as you've got your GMD model and your necessary B field or E field waveforms. Awesome. Okay. Thanks everyone for tuning in. I'll turn it back over to Andrea.
Thanks, Jonathan, for this talk, these research updates. And thank you all for attending this webinar. And let me call your attention for our next webinar that will be in November, on the 20th of November at 3 o'clock. Dr. Miroslav Begovic will be the speaker. And please watch out for detailed announcement coming later. And until then, take care and goodbye, everyone. Thank you for attending.
Bye, everyone. If you have any other questions, feel free to email me, and Andrea will be posting the slides and recording shortly.
We'll
Bye,
do
everyone.
that. Bye.